Let's understand the concept and the math behind Gini impurity and how it all ties together in the field of machine learning, and more specifically the decision tree algorithm. Because earlier we saw another concept, that is entropy. How is entropy used? Entropy is another metric very similar to Gini impurity. When I say similar, similar in purpose to Gini impurity, right? Entropy is also used to decide how a given split should be made on a given decision tree. When you are building a decision tree on a data set, how the tree should be grown, what are the different splits that should be made on a decision tree, is decided based on entropy and information gain. That this concept we saw very clearly in the previous video. All right. Similar to entropy, you can use Gini impurity as well to make this decision of how to create the splits of building the decision tree. In addition to that, there are certain few advantages Gini impurity offers. We will look at that in this one. Now we saw earlier the concept of information gain, and we represent information gain as Ig. Now Gini impurity is also represented as Ig. This Ig is information gain. I'll come to information gain again. We will revisit this concept again after we complete the explanation of Gini impurity. But now understand that Ig is information gain. Gini impurity is also made up of Ig. Now Gini impurity is generally written as Ig, small g. The g goes in the sub. Ig of y. This is the representation of Gini impurity, and the formula is 1 minus summation of all the different categories of the y variable. Say a given variable has k categories. For all the different categories of y, probability of the individual categories, the whole square. This is the entire formula for Gini impurity. That's all there is to it. This is Gini impurity. Now, do you remember what the formula for entropy is? Entropy formula, generally written as h of y, is nothing but summation of, for all the different categories, the same formula applies here. For I equal to 1 to k, we have a negative sign here. Probability of the respective class and log of the probability of the respective class. P log yi, P log yi. Alright, P log P, simply written as P log P, summation of P log P. This is entropy, and there's a negative sign over here. So this is the formula for entropy, and this whole thing is the formula for Gini index. Looks to be too much of math here, so let's understand all of this with the clear examples. Let's take two cases for this, case 1 and case 2. For these cases, let's imagine a data set where your y variable is a binary categorical variable. Your objective is to predict this y. Your y variable is a binary categorical variable. It takes the values zeros and ones. Alright, only two different values, two different categories. You might have a lot of x variables. We don't bother about it right now. All we are concerned with is we want to calculate the Gini impurity of this y variable. How to calculate that? Simply apply it in the formula that we just saw. Alright, so case 1 is the ones and zeros, the two different categories are equiprobable. The same concept would apply no matter how many categories you have. The same concept would apply. Let's compute the Gini impurity for this. The probability of 1 here is equal to 0.5, and probability of 0 here is also equal to 0.5. Alright, both of these probabilities are 0.5. Suppose if it is three categories, suppose your y is composed of three different categories, say category 1, 2 and 3. For it to be equiprobable, all of these would have the probabilities of 0.33. Gini impurity of y here is nothing but 1 minus summation of the probabilities, that is 0.5 whole square plus 0.5 the whole square, which is nothing but 1 minus 0.25 minus 0.25. 0.5. So this is the maximum value. The maximum value of Gini impurity that it can reach is 0.5. On the other hand, in a similar situation, the maximum value that entropy would reach, h of y, the entropy would reach would be, let's calculate it. So minus p log p, isn't it? Minus p log p, which is nothing but minus of 0.5 into log 5, log 0.5. So log here is log 2, log base 2, plus this is probability of 1, and this is also probability of 1. Alright, likewise, probability of 0 is also 0.5. Probability of 0 here is also 0.5. So 0.5 into log of 0.5. If you do the math, this will work out to be 1. Alright. So that is a difference. The difference between Gini impurity and entropy is the maximum values it can take. This is specific to the case where the Y variable contains only 2 different categories. If it contains more categories, then Gini impurity's maximum value can change. Alright. Let's take the case 2 now. Case 2 is one of the probabilities. Let's take probability of 1 equal to 0 and probability of 0 equal to 1. One of the probabilities is maximum. That is this particular case in our data set. The Y here, the Y variable here is composed of just one single class. All of these are ones, or here in this case all of these are zeros basically. Now this is a very pure variable, right? This is what we are trying to measure. In this case, if it is a pure variable, the Gini impurity as well as the entropy in this case should be as low as possible. And in this case, it will reach the value of 0. Let's compute that. So Ig of Y here will be nothing but 1 minus 0 square plus 1 square. 1 minus 1 equal to 0. Alright, this is the Gini impurity. Likewise, entropy of Y will also be equal to 0. When the sample is 100% pure, then both entropy as well as Gini impurity equals 0. So if you try to construct a graph of how the Gini impurity would change as the probability changes, as the probability of one of the categories, let's take the category of probability of Y equal to 1. Probability of Y equal to 1 means this category, one of the categories is 1. Let this probability change between 0 to 1 over here. Alright, at the extreme here it is 0, at this extreme it is 1. When it is 0.5, it would become equiprobable, right? It is at this point both entropy as well as Gini impurity will reach the maximum value. For entropy, the maximum value becomes 1, whereas for Gini impurity, let me draw it here, the maximum value is 0.5. So for Gini impurity, the curve would look something like this. When probability Y equal to 1 reaches a value of 0.5, Gini impurity becomes the maximum, takes the maximum value of 0.5. Whereas entropy would take this value, the maximum value entropy would take will be 1. This is how entropy's curve would look like, and this is how Gini impurity's curve would look like. Now between Gini impurity and entropy, Gini impurity is the default metric when you use packages like scikit-learn. When you are trying to build a decision tree using scikit-learn, it internally uses Gini impurity by default. Of course, you can change it to entropy as well, but Gini impurity is a default option. And the reason for Gini impurity to be used as a default is it does not involve a log term in the computation of the formula. And because of this exclusion of not including log term in this formula, it is computationally more efficient to calculate. Whereas when you are computing entropy, you need to compute a log term. That might require some more additional amount of computation. So my guess is it is for that reason that Gini impurity is kept as the default metric when you are building a decision tree. Hit the like button if you like this video and make sure to subscribe to my channel and click the bell button to be notified of all new ML videos.